In this video, you will see some of the solved problems in section 2.6. First one is give an example of a non-abelian group, all of whose subgroups are normal. So for that, we are going to consider the quaternion group, and we know pretty well that these are their proper subgroups of that quaternion group. And since index of H2, H3, H4 in G being 2, because this is of order 4 and this one is of order 8. 8 divided by 4 gives us 2. So that is nothing but the index of each of these subgroups in G. So we have by one of the results mentioned earlier in the previous video, we have this H2, H3, H4 to be normal in G. And as for H1 is concerned, it can easily be verified that G H1 G inverse is H1 itself for every element G in capital G. So all these subgroups of G are normal in G, but we know that this G is not abelian because I dot J is K, whereas J dot I is minus K. J dot I is minus K. So it is not an abelian group. It is not an abelian group. So next is if H is a subgroup of a group G, it is only a subgroup, and N is normal. N is normal in G. Then we are asked to show that H intersection N to be normal in H only. So whenever this normalcy is mentioned, it is normal in which group, that has to be mentioned clearly. So here given H to be just a subgroup of G and N is normal in G. So H intersection N is normal in H is to be established. You cannot have this H intersection N to be normal in G. So let H be a subgroup of G and N be normal in G. Then to show that H intersection N is normal in G, normal in H, we first note that this is non-empty because it's a subgroup, so E is present. N is normal subgroup, so anyhow it's a subgroup, so E must be present in N. So it must be there in the intersection, therefore intersection is non-empty. Then you consider X and Y in H intersection N, both of them being subgroups. For XY in H and XY in N, X dot Y inverse will be in H and N, and therefore it must be there in the intersection. Or you can simply mention that if it is asked in section A, instead of establishing all this, it can be easily mentioned that if H and N are subgroups, then that intersection is a subgroup. So here H intersection N is a subgroup. Otherwise, in 5 marks question, if it is asked, all these details are to be given. Now, to prove that H intersection N is normal in H, we'll have to consider H in H and an element X in H intersection N. We have to show that H inverse belongs to the intersection H intersection N. It must be present in H intersection N. So we'll consider X in H, and because H is in H is a subgroup, obviously this is a member of H. And because N is normal, X is in N and H is in H, so it must be there in G. So you have H inverse to belong to N. So you have the product H inverse to belong to H intersection N. We have therefore H intersection N to be normal in H. Now next one, if H is the only subgroup of order of H in the finite group G, then we have to show that H is normal in G. See, to show that H is normal in G, this is the technique that is used, that if we are having GH G inverse to be equal to the whole of H, for every G in G, whatever may be your G. In G, if you are able to have this, then your H will be normal. So this is the concept behind in proving that given H is the only subgroup with order of H, then H is normal in G. So let H be a subgroup of the given finite group G, and you take an element X in G. Then you consider X, H, X inverse. Then you can easily prove that this X, H, X inverse is a subgroup of G. Now first it is non-empty because E, which can be rewritten in this way, because any element in this should only be of this form. So you have this, the whatever you have in the middle, that should be a member of H. That is the condition. The middle one should be in H. So you have X, H, X inverse to be non-empty, and for two elements A and B in this, we have A, B inverse to be A should be of this form and B should be of this form, X, H prime, X inverse. And when you consider this, you have actually B inverse, you have like this, and when you have X inverse, H prime inverse, it is H prime inverse and X inverse. So the middle term, namely X inverse X, will give you identity element. So that is not shown here, and this is obviously a member of H, and therefore the whole lot should be present in this collection, and therefore this is a subgroup. Next, we establish a one-to-one correspondence between H and X, H, X inverse by defining a mapping sigma between them, taking any small h to this particular, this element X, H, X inverse for every H in H. Then it can be easily shown that the sigma is 1-to-1 and onto, and therefore the number of elements present here must be equal to the number of elements present here, and so you have order of H to be equal to this, and because H is the only subgroup of with order of H, this XH, X inverse should coincide with H, and that in turn gives H to be normal in G. So proving the sigmas 1-to-1 and onto is very simple. Ontoness obviously follows, and for 1-to-1, by left cancellation law and right cancellation law, image is equal will imply pre-images will be equal. So the fourth one is if N and M are normal subgroups of G with N intersection M singleton E, then we are asked to show that these two elements commute, N and M, where N is any M, any element in N, and M is any element in capital M. So we are given N intersection M to be E, and with that we have to show this. Now we know that whenever we want to show that A equals B in a group G, it is enough we say that AB inverse is the identity element, so that we can easily have this. So it is the same technique that is used here. We consider this as A, this as B, so AB inverse is considered. So NM, Mn inverse is considered, and that is nothing but N inverse M inverse. So this Nm, Mn inverse we have as this is grouped in two different ways. One is grouped in this way, the same element, the same one, but grouped in this way. In the first case, we have, because M is normal in G, we have this to belong to M, and this is we have as such. And because M is a subgroup, M inverse will be a member of capital M, as our small m is a member of capital M. So this will be absorbed, and so you have this to be equal to M. So this is a member of M, and the same technique, but here N is normal, that is used here, and N belongs to capital N, so it will be absorbed by N, so you have this. So the same element belongs to both N and M, so it must be there in the intersection, but the intersection is singleton E, so we conclude that Nm equals Mn. Next is, if a cyclic group T of a group G is normal in G, then we have to show that every subgroup H of T is a normal in G. So we have G to be the given group. G is the given group, and H is a subgroup T of G. We have wish to draw it. So something like this, that you have G, and you have in that T, and in that you have H. What is given about T is it is cyclic. It is cyclic, and we know that every subgroup of a cyclic group is cyclic. So H is cyclic. But our job is to show that. So this will be normal in T, and that is not expected. We want to show that H is normal in G. So let T be the given cyclic group of G, and that is normal in G. That is given. That is normal in G is given. Now we'll consider H to be a subgroup of T. Our job is to show that H is normal in G. Now since T is cyclic, T is generated by A for some A in T. Now since H is a subgroup of T and every subgroup of a cyclic group is cyclic, H must be generated by some A power M, where M is some integer. Now to prove that H is normal in G, we prove that for every G in G and B in H, G inverse BG belongs to H. So this is what we are trying to prove. Now since B belongs to H, B is written as some integral power of A power M. So we can write like this. Now since T is normal in G, G inverse AG being a member of T generated by A, we can write this entire element as A power N, and T is normal means this will be in T. So your now A power N is in T, some integer N. Our job is to show that G inverse BG is in H. So we consider that. Replace your B by A power MK. So you have this. And from here you have G inverse AG. This is, see, whenever we just consider with two elements, G inverse, the power to be 2, G inverse A square G if we have, then we can rewrite this as G inverse A into G. Now introduce one E in between, replace that by G inverse, so that we will have this being rewritten as G inverse A G the whole square. G inverse A G the whole square. So in general, if we consider MK, then this must be rewritten in this way. But G inverse G is A power N. So you have this. So it is A power MKN, or you have actually this being written as integral power of, you can rewrite this as integral power of A power M. So N K or Kn. So you have this being a member of H, and that is nothing but your A power, that is the subgroup generated by A power M, and that is why you have this to be in this. So we have G inverse BG to be a member of H, and therefore H is normal. So conclusion is every proof must be concluded, therefore H is normal. H is normal in G. Next is we have to prove by an example that we can find three groups E, F and G with E contained in F contained in G, with E normal, this is normal in F and this is normal in G, but this is not normal in G. So for that we shall consider D4. Our G in this case is D4. we have these to be the subgroup. All these are already discussed under section 2.4 subgroups. Examples we had a lot. This is one among them. So G is taken as your dihedral group. So in that, these are the subgroups where each row, not row 1, they stand for what is to be mentioned. Now using result 1, you have E to be normal in F. Using result 1, what was result 1? Whenever the index of H in G is 2, H is normal. So H3, if we consider H3, actually H7 is of index 2. So E is normal. E which is taken as H3 is normal is not due to that result 1, but this one is due to result 1. This is actually we'll have to compute. Either you show that G H3 G inverse equals the whole of H3 using the table, or element wise we'll have to consider, and it should be there in H3. G and G inverse should belong to N. The definition has to be used. But H7 is normal in G only follows from result 1. This H3, it is only, yes, see, even for this, E is normal in F, for that we can make use of result 1. We don't have actually H3 to be normal in D4. See here, the number of elements in H3 is 2. Number of elements in H3 is only 2, and number of elements in H7 is 4. So 4 divided by 2, and that is 2. That is nothing but the index of H3 in H7. Index of H3 in H7 is 2, and therefore you can use the result 1 to conclude that E is normal in F. But this E is not normal in G. That is, for that, if we are able to show that for one G in G and N in N, G and G inverse doesn't belong to N. If you are able to show that, then we can easily conclude that that N is not normal. So here for H3 we are going to adopt that definition. So we will consider delta 1 mu 2 delta 1 inverse. Delta 1 inverse from the table is nothing but delta 1 itself. So we have this. Now delta 1 mu 2. Delta 1 mu 2 is row 1, and this is what we have. Row 1 delta 1, row 1 delta 1 is mu 1, but that doesn't belong to H3 because H3 is row not mu 2. So it doesn't belong to H3, and therefore we have got E, we have got E, F and G such that E is normal in F and F is normal in G, but E is not normal in G. Next we have, if N is normal in G and A in G is of order of A, then we have to prove that the order of NA in G mod N is a divisor of order of A. So we'll consider order of A to be N, then A power N is the identity element. Name that is equation 1. Let N be normal in G, and let order of NA, this right coset which is present in G mod N, to be M. Then M is the least positive integer such that NA power Mn is identity element in G mod N is N. So we have this. Now we claim that M divides N. So order of NA is taken as M, and that should divide order of A. That is our problem. So for that we'll consider the element NA raised to N. So because N is normal, repeatedly applying that product of two right coset is again a right coset, because N is normal, that can be used. So we have this step, and When you consider A power n, we have by equation 1 that it is E, but E being a member of n, it will be absorbed by n, so you have n. So Na raised to n is n, Na raised to m is also n, of which m is least. So least must divide any other. So based on that, we conclude that m divides n. Now in the next problem, we are given G to be this group. This is given to us under matrix multiplication, and n is given to be in this collection. We are asked to show that n is normal in G and G mod n is abelian. So you consider any small g in capital G, which is in this way, and any small n in this. We will, because b is used already, we shall name it as some b prime, where that b prime belongs to R. That b prime belongs to R. Now we'll consider G and G inverse. G inverse can easily be computed. We have, after computing this G inverse, how do we compute that? We have the determinant of this that should be put in the denominator AD, and in the matrix, which is 2 cross 2, we'll have to have this to be D and interchange the diagonal elements and put a minus sign for this. So this is the inverse, and taking this one inside, we get 1 by A minus B by AD, and 1 A gets cancelled. So we have this is you have D here. This is AD. So you have A. This is D, so D gets cancelled, so you have this, and here you have your A getting cancelled, so it is 1 by D. It is actually 1 by D. So when we multiply all this, this is what we get, D here, and so you have matrix multiplication, so performing that, this is what we get. So in this B by D, minus B by D and plus B by D gets cancelled, leaving this. So it is 1, 0, 1 in these entries, and this is A B prime by D, and this definitely belongs to n because A, B prime, D are all in R, so this must be in R. So we have G and G inverse belonging to n, therefore n is normal in G. And of course, this n must be subgroup that needs to be established. So that is not established here. You need to have your n to be non-empty, because sub B can be any element. Choosing that as 0, your identity element is present, so n is non-empty, and we'll have to consider two elements, say n and n prime, in capital N prime, and show that the closure holds and inverse is also present in that. So R together we can consider and establish that to be a member of n. So that part is not established here, showing that n is n is a subgroup. Only normalcy condition is verified here. Next, to prove that G mod n is abelian, Gn, this is a right coset, it's a set of elements of this form. So you have the product on computation giving you this, and similarly G prime n on computation gives you this. So when we consider G, the product of Gn with G prime n, then this is what we get. This is what we get. And similarly, when you consider G prime n Gn, which is same as G prime Gn, so this is what we get. This on simplification gives you this. Now when you look at the elements of this and the elements of this, the main diagonal elements are the same, and here you have the same 0. The change is only here in the first row, second column element. The change is only here, but remember that all of them are members of R. So the whole lot will be a member of R. Here also the whole lot will be a member of R. we cannot equate each element wise. We cannot have, see, something like this that you have. If you have, say, the set consisting of 1 2 3 and the set consisting of 2 1 3 as sets, they are equal, but you cannot equate 1 to 2, 2 to 1, of course 3 is 3. So you cannot equate element wise, but as sets they are equal. So likewise, G and G prime n as sets, they are equal. Because this G n, G prime n and this are equal, we conclude that G mod n is abelian. And there is another way to prove this result by defining sigma a mapping, which will be discussed only in the next section, homomorphism and all, and they are yet to be discussed in our videos. So we just give a hint that how else the same problem can be proceeded. You define a mapping sigma from G to R star cross R star. So that gives us sigma is defined in this way. Sigma of G is sigma of any arbitrary element is of this form. We define that to be the ordered pair AD. Then this is obviously onto, because any pre-image will have any element will have number of pre-images with B varying. So it is onto, and homomorphism can also be proved that sigma of G prime is same as sigma of G into sigma of G prime. Homomorphism will be discussed only in the next section. And when we find the kernel, this is what we have. All those the 2 by 2 matrices with the entries A, B, 0, D, such that sigma of this is the identity element of the codomain. This R star cross R star is also a group with identity element 1 1, ordered pair 1 1, and this how sigma is defined. This is how it is defined. So you have AD being equated to this, so that gives A to be 1 and D to be 1. So you get your kernel to be these elements, and that is n. So n is normal in G. So since sigma from R star to R star is R star G to R star cross R star is an onto homomorphism with kernel n by first isomorphism theorem, which are to be discussed only in section 2.7, not yet discussed in our videos. So G mod n is isomorphic to this. So since this is abelian, we conclude that G mod n is abelian. So this is another way of proving the same problem. Next is let n be normal in G and H be a subgroup. Then we have to show that NH is a subgroup of G. We don't have H to be normal, just H subgroup. We have to show that this collection is a subgroup. Now we have to first show that NH is a subgroup. For that, it is non-empty, because E can be written as E into E, that belongs to NH, so it is non-empty. X and Y in NH should imply XY inverse belongs to NH. That is one way of proving that NH is subgroup. Then there is another method which is easier than the traditional method, that we make use of the criterion to have H and K to be subgroup. HK to be subgroup, HK must be equal to KH. That is one of the theorem that we established in section 2.5. So we make use of that technique to prove that NH is a subgroup. So to establish this, we have to show that this is contained in this and this is contained in this. So you consider X and NH, you can write like this. Introduce E here and replace that by HH inverse and group like this. Because N is normal, this must be present in N, and this is obviously in H. So your NH is contained in H and name that as 1, and you consider y in Hn. This y can be written as H and E. Replace E by H inverse H and then group like this, and because n is normal, it is in N, and this is obviously there in H, so you have your y to belong to NH. So y in Hn implies y in NH, so Hn must be contained in NH. Name that as equation 2. So from 1 and 2 we conclude that NH equals Hn, and so NH is a subgroup of G. Next is, if N and M are normal in G, then NM, the product, is normal in G. Just now we proved that NM is subgroup. So to prove that NM is normal in G, we consider G in G and X in NM. So you have Gx, G inverse to be like this. Introduce E in between and replace that by G inverse G, so that this will be a member of capital N and this will be a member of capital M, and that shows that your M, the product NM, is normal in G. So with this, the solved problems in section 2.6 end. So in the next video, we'll have the concepts from section 2.7 homomorphisms. Thank you.